Back, everybody. We're going to continue talking about Chapter 9, and at this point we're up to Section 9.3. So we're going to be talking about hypothesis tests for population proportions. We just got done talking about hypothesis tests for population means. Conceptually, this section is essentially identical, so we should be able to get through this pretty quickly. We're just going to focus on some different formulas. So let's talk about this real quickly. When we have non-quantitative data, we typically analyze proportions. So when we're talking about non-quantitative data, we're talking about data that has no quantitative or numerical meaning. So for example, if I ask you who you plan to vote for in an upcoming election, think about the last presidential election, you could respond with either Obama or Romney. There's nothing quantitative about that. So when we analyze that type of data, we deal with proportions. So I can figure out the proportion of people who are going to vote for Obama and the proportion of people who plan to vote for Romney. So all the tricks that we learned in the previous section apply here. And as I'm mentioning right over here, we just have to adjust the formulas that we use for standard error and for Z. So previously we computed standard error of the mean using this formula, and then we computed Z to transform a sample mean into a Z-score. Now we're going to compute standard error of the proportion, which is just like standard error of the mean. Standard error of the proportion will tell us on average how close the sample proportions come to the true proportion, the true population proportion. So it's telling us how much error to expect from one sample proportion to the next. We'll feed that into our formula for Z, just like we fed the standard error of the mean formula answer into the formula for Z. And here we're going to stick in the sample proportion and the population proportion, just like we had the sample mean and the population mean. So I hope you're seeing these formulas are essentially identical to these formulas, at least conceptually speaking. We're just moving from a discussion and calculations regarding means to a discussion and calculations regarding proportions. So let's try some examples. Let's talk about a political poll. A political candidate commissions a poll before a close election. Using a random sample of 400 likely voters, the poll finds that 204 respondents support the candidate. Does the candidate have a statistically significant lead? Test with an alpha equals 0.05, one-tailed. So we're going to do a one-tailed test in this particular example just to get some experience. And in this particular case, we are predicting that our candidate actually has a lead. So the way we'll set up our hypotheses, remember we always have competing hypotheses, a null hypothesis and an alternative hypothesis. Our null hypothesis is going to state that the true population proportion of people who support the candidate equals 50%. So that's based on the idea that there are no differences between the candidates. Nobody has an edge. The alternative is going to be that the population proportion of people who support this candidate is greater than 50%, stating that this candidate actually does have a lead coming into this election. All right, let's collect some evidence, and I've already provided some evidence here. We see that 204 people out of the 400 support this candidate. So we can compute a sample proportion. In this case, 204 people over 400 equals a proportion of 0.51 or 51%. And we can verify that real quickly. 204 divided by 400 equals 0.51. Okay. So from there, we can now start to think about probability. Because what's the probability that we would find a sample proportion this extreme just by chance? We're essentially comparing the 0.51 with the 0.50. And I'm sure you can tell this is not that big of a difference. Now we've learned we don't necessarily need big differences for them to be statistically significant. But I'm having a sense here that this difference is probably going to be ending up being the type of difference that we would expect to find just by chance. At least that's my prediction. And I think when you go through these steps, you should try to predict what you think you're going to find as well. Because if you find what you thought you were going to find, it's just further evidence that you're on the right track with your thinking. So we need to consult, not in this case, the distribution of sample means, but a distribution of sample proportion. So theoretically, it's the same thing. And we learned the last time we talked about how to find these critical values that mark off the critical regions or rejection zones. If we're using an alpha of 0.05 one-tailed, we know that they're marked off at 1.645 or if we're doing a left-tailed test, negative 1.645. And you'll always have a table that will remind you of that. So now we need to figure out where is a proportion of 0.51 in this distribution. Right in the middle, we have a z-score of 0, and that represents where we'd have that population proportion of 0.50. Because remember, this distribution of sample proportions is always created based on the idea that the null hypothesis is true, and that the true sample proportion is 0.50. The true population proportion, that is 0.50. And most of our sample proportions would be right here. That's why we have this high point, this hump of our distribution. Most of the sample means will be right around 0.50, which is where that true population proportion is according to the null hypothesis. So where's 0.51? Is 0.51 the type of sample proportion that we would expect to find just by chance? Or is 0.51 over here the type of sample proportion that is very extreme and we would not expect it by chance if the true population proportion is 0.50? Well, the only way we can figure that out is to transform it into a z-score. So let's do that. The first thing that we need to do is compute this standard error of the sample proportion. And we're going to use this formula. This portion looks at the population proportion multiplied by 1 minus the population proportion divided by our n. In this case, our n is 400 voters. And we take the square root of the whole thing. So let's just walk through the steps real quickly. We see that the population proportion under the null hypothesis is 0.50. So we take 0.50 multiplied by 1 minus 0.50, which is 0.50, divide by our n, which is 400. 0.5 times 0.5 is 0.25. We divide that by 400. And this is where let's step through it. Usually in our class, we try to round things to 2 decimal places. But we often can't when we're dealing with these really small numbers. If you take 0.25 and then divide by 400, you get a really small value, 0.000625. Obviously, if we rounded to 2 decimal places, we'd have a value of 0, and that wouldn't capture very well our real measurement here for the standard error of the proportion. Clearly, we expect some differences from one sample proportion to the next. We don't expect very big differences in the end. So in this case, we're going to take that entire number, and we're not going to round it, and we're going to take the square root just to make sure that we get an accurate number in the end. So we'll have to do that when we're dealing with these really small numbers. No big deal. So take the square root equals 0.025. All right. Well, that is our standard error. So once we find our standard error, we know that we can then feed that into our formula for z. So now we know how much the sample proportions differ on average. Let's see how big the difference is between our sample mean and the population mean, which is based on that null hypothesis. Our sample mean was equal to 0.51. We computed that right here. And of course, the population proportion based on the null hypothesis was equal to 0.50. So we see a difference of 0.01, about 1%. So we look at the differences that we actually observe, and we divide by the differences between those proportions that we expect just by chance. So let's verify that. We have 0.01 divided by 0.025, and that equals 0.4. So you know by now a z-score of 0.4 is not very large. Z-scores are starting to get large once they get to like 1.5, 2, and after that. So here right in the middle we have a z-score of 0. And right about here, so we have a z-score of 0.4, and that represents where our sample proportion is of 0.51. So we can see it has not gotten into our critical region. It has not surpassed this value, which marks off where our critical region begins. So ultimately, we're not going to reject our null hypothesis because these critical regions we know are also known as rejection zones, and the only time we reject our null hypothesis is when our sample data is in that area. And when it's in that area, it shows us that it's a sample value that's very unlikely to be found by chance. We just found a sample value of 0.51 that's quite likely to be found just by chance, even if the true population proportion is 0.50. So we're going to fail to reject the null hypothesis. Let's formalize those results in step 4. Z equals 0.4 does not exceed the critical value of 1.645. So the probability of finding this result by chance is greater than 0.05. And that was our burden right there. We needed this much evidence. We were not able to rule out chance. The probability of finding our data is greater than 0.05, so we couldn't rule it out. The result is not statistically significant at the 0.05 level. So in other words, we fail to reject the null hypothesis, and if we're going to fail to reject it, that means we're keeping it, we're retaining it. So our interpretation can also be found by coming up here and looking at and seeing which hypothesis we're keeping. We're keeping this one, and it says the true population proportion of people who support the candidate equals 0.50 or 50%. So our conclusion is that our candidate really doesn't have majority support. Only about 50% of the people, according to our best guess at this point, support that candidate. Let's go through another example. We should just need one more, and I think you'll probably have a good idea of what's going on. These examples are just like the examples in 9.2, except we're using slightly different formulas. Let's look at this particular one. It says a researcher randomly selected 750 people, of whom 92 were deemed to be left-handed. Use the sample data to test the claim that 10% of the population is left-handed. So we often hear that number thrown around, 10% of the population is left-handed. Well, truthfully, I don't know what that's based on. I don't know what kind of research was done. So someone did some research that we're reading about here to test to see if that commonly understood number really has some evidence to support it. So let's do a two-tailed test, because that makes a lot of sense. We don't really know if the true population proportion of people who are left-handed is going to be less than 10% or greater than 10%. Theoretically, the results can go in either direction. That's why two-tailed tests are typically done. That's why they are the default option. Let's set up our hypotheses. We always have two competing hypotheses. Let's start with our null hypothesis. Our null hypothesis always states there are no differences, no effects. So this would state that the true population proportion of lefties equals 10%, just like has been claimed. Our alternative hypothesis needs to include all other options, and that would mean that the true population proportion of lefties is something other than 10%. Well, we're going to be using an alpha of 0.05 for a two-tailed test. So that will tell us how much evidence we need. First, let's actually talk about the evidence that we have. We found that 92 people out of the 750 are left-handed. So we can easily compute a sample proportion. We take those 92 people, divide by the 750 overall, and we find a value of 0.12 or 12%. Let's verify that real quickly. 92 divided by 750 equals 0.122. We can just round that to 0.12 or 12%. All right, so now we know where we are with the evidence. Let's figure out what kind of evidence we need to reject the null hypothesis. Because we have to determine, is this the type of difference between 10% and 12% that we would just expect by chance? Or is that the type of difference that's really extreme and we can rule out chance as a reasonable explanation? The only way we can figure this out is by looking at a distribution of sample proportions. Right there in the middle, we have that true population proportion based on our null hypothesis of 10%. And that would transform into a z-score of 0. We need to figure out where 12% is. Is 12% the type of sample proportion that we would expect to find quite often just by chance? Or is it in this critical region and we would find that it's actually pretty extreme and we wouldn't expect it by chance very often at all? Well, the only way we can figure out where it is to transform it into a z-score. So the first thing we need to do is compute our standard error. So we'll use our formula. And of course, the p's are based on our null hypothesis and that true population proportion value. If we take 0.10, we multiply by 1 minus 0.10, which would be 0.90. 0.10 multiplied by 0.90 equals 0.09. We're dividing by our n, which is 750, and we need to take the square root of that whole thing. So let's just verify this. We're in that situation again where we're dealing with very small numbers. So we'll take a 0.09 and then divide by 750, which is our sample size. That equals 0.00012. So again, it's not going to help us to do any rounding there. So let's leave that entire number in our calculator and then finally take the square root as the formula advises. That equals 0.010, so we'll just round that to 0.01. All right, so now we know on average how much the sample proportions differ from that true proportion. So it gives us a sense of the variability that we expect between sample proportions just by chance. Now we can feed that into our formula for z. So now we're going to look at how big are the differences we actually observe between our sample proportion of 0.12 and the population proportion based on the null hypothesis of 0.10. So these are the differences that we're actually observing between those two values. relative to differences between sample proportions that we expect just by chance. That gives us a z-score of 2. Now we know a z-score of 2 is starting to get relatively large. When we try to map it out here, again, we have a z-score of 0 right in the middle. Here's where our critical region begins with a z-score of 1.96. And we found a z-score of 2, which is in this critical region. Remember, a z-score of 2 just represents another way of saying 12%. That z-score of 2 represents where our sample proportion is. So 12% is in the critical region. The critical region is also known as a rejection zone. So we're going to reject the null hypothesis because sample proportions in here we would not expect to find very often just by chance. And in fact, they occur so infrequently, we start to question if the null hypothesis is true. So we have enough evidence to rule it out and take on the alternative that the true population proportion of lefties is something other than 10%. And because we found a value larger than 10%, we can conclude that more than 10% of the population is left-handed based on this evidence. Let's formalize that in step 4. Z equals 2 exceeds that critical value of 1.96. So the probability of finding this result by chance is less than 0.05. So we have effectively ruled out chance. The result is statistically significant at the 0.05 level. Again, we reject the null hypothesis, which means we are literally saying that we no longer believe that this is true. We're going to take on the alternative, and now we believe we have evidence that this is true. The true population proportion of left-handed people is something other than 10%. Well, our best guess is to coincide with our sample data, and that is that the true proportion is greater than 10%. So we conclude that the true population proportion of left-handed people is greater than 10%. All right, well, I hope that you're starting to get the hang of things here. That concludes this particular section and the key content. For now, that is all.